Welcome students. We are studying the topic phase equilibrium. Now we are in this lecture 3 where we are studying the two component system. So up till now we have studied the one component systems. In that we have studied the water system and the sulfur system. Now let us see the systems which consist of two components, and for that the example is the silver lead system. So let us see what this system is and the details of the phase diagram and all the things. So the example for this is the lead silver or silver lead system. Again, if you see here, the name itself indicates that this system has two components, and the two components are lead and silver. Again, if we consider the number of phases, this system consists of 4 different phases: solid silver, solid lead, solution of molten silver and lead, and again the vapor phase. Now if you see here, this system, that is lead silver system, if we consider the components which are there in the system, that is the two components are there, that is silver and lead. So you can imagine, आप भी उसको imagine कर सकते हो, सिल्वर और लेड को उसका जो बॉइलिंग पॉइंट है वो बॉइलिंग पॉइंट बहुत ही ज़्यादा है, इसलिए वेपर फेज, इस सिस्टम में वेपर फेज absent समझा जाता है, as the boiling points of silver and lead are considerably high, so the vapor phase is considered to be practically absent. Thus, this system is considered to be a condensed system with 3 phases. Though there are 4 phases, this vapor phase is practically absent, so we consider this system as a condensed system. Now, in such a system, pressure can have no effect on the system. Thus, we need to consider only the 2 remaining variables. So if you consider the 3 different variables, then one variable, that is pressure, has no effect. Therefore, we have to consider here the 2 remaining variables, that are the temperature and concentration. So when we consider temperature and concentration, that the 2 remaining variables, then we have to draw here the phase diagram, that is the complete TC diagram of the system is shown, or you can see the diagram here. So if we see the diagram, then you may understand certain things, or we can have the salient features of the diagram. Just we have considered the salient features of water system, we have considered the salient features of sulfur system, and this one, that is the silver lead system. Again, you can understand here. So if you see the TC diagram or the phase diagram of this system, that is temperature against composition. So there are certain salient features you can see in the diagram. That is, the first one is there, that is there are 2 curves are there, that is AC curve and BC curve. Again, joining these 2 curves, there is one point, that point is C, and this point is known as the eutectic point. Students, you can see here, or you can understand here, is that here there is not the triple point, but here it is eutectic point. But in water system and sulfur system, there are triple points. Okay, in water system there is one triple point, and in the sulfur system there are 3 different triple points. But here this point is known as the eutectic point, because there is union of these 2 curves, therefore it is known as the eutectic point, because here 3 different curves are not meeting, therefore this is not a triple point, but it is a eutectic point. So this is the second salient feature of the diagram. Now the third salient feature is there, that is the three areas, that is above ACB. See here, above ACB this area is there. Then the area under or below AC. So this is the area that we have to consider here, and area below BC. So BC curve is there, and whatever the area below BC is there, that this area is there. So this will give you, that is the two curves, one eutectic point, and the three different areas will give you the complete features of this phase diagram. Now let us see one by one. Curve AC. Now this curve AC is known as the freezing point curve of silver. You can see here in the diagram, A represents the freezing point or melting point of solid silver, that is shown in the diagram, that is 961 degree. So this is the temperature. Okay. So, and the curve AC shows that the addition of lead lowers melting point along it. See here, along this curve AC, if you see here, this is the highest temperature where the molten melting point of solid silver is there. Now if you see here, you can see in the diagram also, so lead is added here. See here, here is 0% lead is there. Now 100% of silver is there, 961. So 0% of Pb is there. Now I add a certain amount of Pb, small amount, small amount, small amount. Then when I add the amount of Pb, that is lead, to the silver, then whatever the temperature of the system is there, that temperature decreases. So this decrease in temperature can be seen along curve AC. So see here, the A that comes to C, and here the temperature is 303 degrees centigrade. So if you see here, along AC there are two phases in equilibrium. So if you see here along AC, see here, this is one phase and this is another phase. So there are two phases in equilibrium. So that is solid silver and solution of silver and lead. So solid Ag and solution of silver and lead, and along this curve again silver is there. So if you see here, again we will consider the second curve, that is BC. And this curve is known as the freezing point curve of Pb, that is lead. Now again if you see here, B represents, again see here, B represents the melting point of solid lead. So this is the solid lead melting point of at the point B, where the temperature is 327 degrees centigrade. Now if you see here, the curve BC shows that the melting point is lowered. Again see here, the melting point is lowered. So you can lower the melting point by addition of silver. If we add silver, now silver is in 0%. Now if we add silver, that is 2.5 of Ag here if the point is there. And if we add silver, then the melting point of lead is decreased. And along BC, the phases in equilibrium are solid lead and solution. So you can see here, solid lead and solution. So that if you see here, these are the two curves, that is AC and BC. Along AC and along BC, there are two phases in equilibrium. So if I apply the phase rule equation, now see here, our regular phase rule equation is F is equal to C minus P plus 2. But here whatever the phase rule that we are using is F is equal to C minus P plus 1. Why this is there? Because whatever the vapor phase that we have considered as absent or practically absent, then one of the degrees of freedom is considered to be absent, that is pressure. As vapor phase is absent, pressure is absent. Therefore we are using here the condensed phase rule equation. Condensed phase rule means instead of F is equal to C minus P plus 2, we are considering the condensed phase rule as 1, because instead of taking 2, we are taking here 1, that is F is equal to C minus P plus 1. So that components are 2 and phases along the two curves are 2, then 2 minus 2 plus 1, that will give you 1. Means we require only 1 degree of freedom means to explain the system along the curves of the lead silver system or silver lead system, we require only 1 degree of freedom. That is, the system at the curves AC and BC is monovariant. I think you have understood up till this now. Now let us see the eutectic point, very typical point here. So the eutectic point C is there, where the two curves that unite or they have a union, and that is called the eutectic point. Now if you see here, at this point, you can see in the diagram also, there are at this point 3 phases, that is solid silver, then solid lead and solution are in equilibrium. So this is very typical point where the 3 phases are in equilibrium. So if I want to apply the phase rule equation, that is F is equal to C minus P plus 1, which is nothing but the reduced phase rule equation, we get the value of F as 0. Means the system, that is silver, lead and solution, is monovariant. Means it requires, it is non-variant. Means we don't require any degree of freedom to explain the eutectic point C. So at point C, again the variables, that is temperature and composition, are fixed. So you can see here, this is very typical point where the composition of lead is 97.5 and the composition of silver is 2.5. Okay, again if you see here, the temperature condition at this point is 303 degrees centigrade. Means when the temperature 303 degrees centigrade is attained, at that temperature exactly the composition of lead is 97.5 and 2.5 of silver is there, and at that composition and at that exact temperature we get eutectic point. Again, if we raise the temperature above the eutectic temperature, the solid phases silver and lead disappear, and if we cool below it, you will land in the solid AgPb area where solution phase is non-existent. Means देखिए, ये पॉइंट के थोड़ा इधर उधर जाओगे तो whatever the typical situations of this point are there, ये आपको नहीं मिलेंगी. आप टेम्परेचर रेज करो यूटेटिक टेम्परेचर के ऊपर, फिर सॉलिड फेजेस ऑफ सिल्वर एंड लेड ये वेनिश हो जाएंगे या डिसअपियर हो जाएंगे. और अगर टेम्परेचर कम करते हो, इसको कूल करते हो, तो आप सॉलिड एजीपीबी एरिया आपको मिलेगा और ये नॉन एग्जिस्टेंट है. नेक्स्ट, द silent feature of this diagram is the different areas, so that we will take into consideration the area above ACB. So see here, ACB. So the area above ACB is this one. So we will consider this area. Again, see here, this region is nothing but having a single phase. Then the solution of molten Ag and Pb. So if I want to apply the reduced phase rule equation, then F is equal to C minus P plus 1, and that is equal to 2 minus 1 plus 1. So that F is equal to 2 means the system solution AgPb is bivariant. Now next area, the area below AC and BC. So you can see here the area below AC and BC. Then if you see here, the system represents the phases Ag plus solution, while the below BC it represents the phases Pb plus solution, means lead plus solution. The area below the temperature 303 degrees centigrade represents solid Ag plus solid Pb. So if you see here, whatever the different areas are there, area below AC and BC, we get the two phases which are in equilibrium. Means आप अगर AC के नीचे का एरिया देखोगे तो दो फेज है, और BC के नीचे का एरिया देखोगे the solid Pb and solution of Ag and Pb is there. Again, if you see here, solid Ag and solution of Pb and Ag is there. So दो एरियाज है, सॉरी दो फेजेस इक्विलिब्रियम में है. सो अगर हम phase rule equation, that is the reduced phase rule equation, if we apply, then f is equal to c minus p plus 1, so that components are 2 because two component system is there and the phases are 2, that is 2 minus 2 plus 1, that will give you 1. Means the meaning of f is equal to 1 is the system requires 1 degree of freedom, that is this, it is monovariant. I think you may have understood the different salient features of the diagram. Now let us see the only thing that remaining in the diagram that we have to explain is this dashed curve or dashed line xy. Now let us see what is this dashed line xy. So you may see in the diagram, this is actually the process of recovery of silver from argentiferous lead. See here, recovery of silver from argentiferous lead. So at the high temperature, both silver and lead are getting mixed, and to separate silver from lead, this is actually the process. That xy dashed line is nothing but the Pattinson's process for the desilverization of argentiferous lead. So how we can explain this is the argentiferous lead, which consists small amount of silver, that is less than 0.1%, is melted well above the melting temperature of pure lead. Pure lead melting temperature is 327 degrees centigrade. Now let आप देख सकते हो, the point X represents the system molten lead. So in the diagram, this molten lead is considered at point X. It is then allowed to cool. See here, temperature decrease हो रहा है, temperature decrease होता है. Then it allowed to cool when the temperature of the melt falls along dashed line. So whatever the temperature which is falling, that can be considered along this dashed line xy. So as the temperature corresponding to y on the curve of BC is reached, right? So this is the temperature. When y point comes on this curve, that is BC, then if you see here, solid lead at this point begins to separate, and the solution would contain a relatively larger amount of silver. Again, on further cooling, more of lead separates and we travel along the curve of BC. So more of lead separates and we travel along curve BC. And when we travel along BC, we come at the point C, and lead in this way is continuously removed by means of ladles, and the percentage of silver in the melt goes on increasing. And what at point C, what happens? An alloy of silver and lead is obtained, that is containing the amounts as 2.5% of Ag and 97.5% of Pb is obtained. So you can see at point C, 97.5% of Pb and 2.5% of Ag is obtained, and in this way this is treated for the recovery of silver profitably. So actually this Pattinson's process for desilverization of argentiferous lead is an industrial process, and this is one of the application of the phase rule for the what you call it as industrial desilverization of argentiferous lead. I think you may have understood